Welcome to the project demonstration of solar battery charging by using bidirectional DC to DC buck boost converter. So the main features of this project is whenever we are going to charge a battery pack with help of renewable source solar panel, so there are chances of low voltage and low current will be available because it is a source providing the voltage which is based on the sun intensity on the solar cells. So if the sun intensity is more, then it will provide the more voltage. If it is less, so less voltage with less current. So whenever it's getting the sufficient current voltage to charge a battery pack, then there is no issues. Directly the solar panel is providing sufficient current along with the voltage so that we can get the maximum power to charge a battery pack. So that will be directly to the battery pack system using the charging circuit. So then there is another case whenever the sunlight is not available more in the morning season below 10 o'clock or after 4 o'clock till 6 o'clock. So at this duration the sun intensity is very less, so that there is no sufficient voltage will be generated from this solar panel. And in the rainy season also it can't get the sufficient sunlight and means sufficient sun intensity, so it can't provide us the maximum voltage to charge a battery pack within the respected time. So that's there our project is providing the solution to that by using this DC to DC buck boost converter, where we are going to use the LEDs as application. So for example, whenever we are getting the voltage from the solar panel, if it is sufficient to charge a battery pack, parallelly if you are getting the more than sufficient voltage which is enough to charge a battery and control the load, then directly our DC to DC converter, which will act as a buck and boost converter when it is above 14.5 volts, means generally we are using the 12 volt solar panel, though it can generate up to 17 volts. So you can see the rated voltage here, you can see that VRMS is 17.4 volts and maximum of 20.40 in open circuit voltage. So there we can get the maximum voltage with less current so that the power will be reduced. In order to maintain the maximum power, we are making use of this DC to DC buck and boost converter. Whenever the voltage is more than the threshold value, then the system will acting as a buck converter and the remaining voltage will be parallelly distributed to the load of LED as well as a battery pack, so that there is no wastage of power by using this DC to DC buck boost converter. In the same manner, if the voltage is getting less than 12.5 and more than 9.5 volts, then we need to do the boost operation. There it will equally distribute the voltage to the load by providing the less current with less voltage to the load and more current sufficient voltage to the battery pack to charge this system. So here we are using 12 volt 5 watt solar panel and 12 volt 2 amp battery pack, and next 12 volt 3 watts of LED load we are using. And this is the buck boost converter which will consist of two MOSFETs. One is a series MOSFET, another is a parallel MOSFET. So the parallel MOSFET which is connected between the input and output, which will acting as a boost converter MOSFET, and whenever the another MOSFET is connected in series in the positive polarity, that will acting as a buck converter. Means when we are operating the series MOSFET, then the circuit will acting as a buck converter. When we are controlling the parallel MOSFET which is in between the input and outputs, then that particular MOSFET will be acting as a boost converter. So with the help of input output capacitors along with the inductor circuits. So the capacitors are used to provide the maximum voltage and inductor is used to provide the maximum current. So this is the main operation of this buck boost converter along with the operation, and our microcontroller is continuously measuring the voltages of the solar panel and the battery pack. So this is the battery pack voltage sensor and the solar panel voltage sensor. Both consist of 10 kilo ohm, 1 kilo ohm. So nothing but the potential divider circuit which will divide the voltage which is given as input to the voltage sensor by 10:1 ratio. Means whenever we are providing 10 volts DC, the output of this voltage sensor is 1 volt. So in the microcontroller we programmed in such a way that the multiply will be done by 10 so that we will get the exact input voltage to the voltage sensor. So that particular voltage continuously monitoring on the LCD. That's the first task. And the next task is, if the source voltage is greater than the battery voltage, then we are distributing the source voltage to the LED as well as to the battery pack. Whenever there is no sufficient voltage coming out from the solar panel, then in order to provide continuous power to the load, the battery will be switching from the solar panel to to the battery pack, so that the load will be switching between these two continuously, whichever the voltage is more than the another source. So here we are using the solar panel and the battery pack is the main sources and LED is the load we are using. And one more source to charge a battery pack is that is a transformer. So this is the only secondary source to charge a battery pack, as if there is no sunlight while we are demonstrating of the project, we can't place the kit under the sunlight always. So that's why we are providing this transformer to charge a battery pack whenever we have the demonstration. So for that, generally just before demonstration of the project, we need to charge a battery pack full charge, so that we can execute the project without any malfunctioning. And connect the transformer over here, so that we can see the T. So it's a T by S. Connect the transformer and on the power supply to this gauge, the transformer. The light indicated battery is charging. Sorry, we need to connect the B over here. So check clearly, I'm repeating that. T by S, disconnect the solar panel, connect the transformer, and disconnect this A from this A slot and connect the B at this A slot, so that now the battery is charging. So it will take around 5 to 6 hours till the duration we should keep the battery under charging. And after that, while execution of the main project, disconnect the B from the A to from the charging circuit and connect the B to the B slot and A to the A slot. And now you can disconnect the transformer and now connect the solar panel. Right, so this is the main closed loop. So controller continuously measure the solar panel voltage, battery voltage, and buck boost converter. It will do the operation whenever it is sufficient to boost or whenever sufficient to buck. So that will be done by the microcontroller directly. So we have interfaced these two voltage sensors at A0, A1 and LCD at pin number B2 to B7 and C6, C7 for the MOSFET circuits of the microcontroller, which is acting as a buck boost operation. So now let us check the final output after disconnecting the transformer. Now we can on the power supply to this microcontroller, which will continuously monitoring the voltages and displayed on the LCD screen. So welcome message will be displayed on the LCD screen, and then after see we can see that battery voltage is 12.29 but the solar voltage is 0.64. as we can see the low intensity coming out from the charging circuits. Previously when we connect the transformer we got the more intensity. Now it is less because of there is no sunlight, there is no maximum intensity of the light on the solar panel. That's why we are getting the low voltage. If you place any torch light on the solar panel, so we can see the voltage will be a bit increased than the previous one, right? You can see that 0.86, so like that. Okay, so now when we are getting the more voltage on the solar panel, the system doesn't know that whether you connect the solar panel or a battery pack or a transformer. So now we need to provide the alternating voltage just for demonstration, like we are switching between the battery source and a solar panel source to provide the uninterrupted power supply to this LEDs. So for that just I am disconnecting this. Anyways, when I disconnect that also, as we are getting the 0 volts from the solar panel available voltage, right? Slowly the capacitor will be decreases, so the solar panel voltage is 0.21, though the mode battery was connected to the load. So whenever the particular source, so for example if I insert the transformer, though we are getting the maximum voltage, that but the microcontroller think that I am getting the more voltage from this source, that is the solar panel. So when the sufficient voltage is getting from the solar panel, then we can see that the switching was happened between solar panel to the battery and load. Now you can see that solar to battery and load, the mode is now. Why? Because we are getting more voltage from the slots, whatever we connected over here, the solar panel, the transformer, but the system is getting the more voltage from this slot. That's why it is connecting the load and battery to the slots to charge the battery as well as to utilize the power for the loads. So you can see that the battery voltage is 12.50 but the solar panel voltage is 13.5. Okay, so in this manner the bidirectional buck boost converter will use it to achieve the maximum power utilization whenever we are using the renewable sources to charge a battery pack and to utilize the loads directly. Again, we are switching to that. Okay, thank you.